Well, let us continue our discussion on the TTT diagrams. So, I have shown you that the cooling rate determines the transformation and also the product. As you cool slowly, you can form coarse perlite or fine perlite, and once it is cooled fast enough to bypass the nose of the C curve and kept at a isothermal holding temperature, something from 280 to 450 degrees Celsius temperature, magnetic transformations happen, and the type of product will depend upon the holding temperature for barytes. And lastly, I told you that if I cool it fast to bypass the nose of the C curve and to a temperature below martensitic start temperature, martensitics will form. So, that means if it is cooled rapidly enough to bypass both the perlite and the magnetic transformations, then the third product, martensites, will form. And this formation of martensites is completely independent of the time. It depends only on the temperature to which it is cooled. As you see, there are three lines here: MS, that is the martensite start; M50, where the 50% martensite forms; N90, where 19% martensite forms. Remember, martensitic formation leads to a lot of strain in the matrix, and this strain, as in the matrix, obviously elastic strain and plastic strain in the martensites, these are actually leads to increase of the energy of the system, and therefore the transformation from austenite to martensites has never been complete, because the strain energy, which is a positive part of the energy, will be consuming part of the chemical free energy available for the transformation. And so once the strain energy is large enough to take over the whole chemical free energy available for the transformation, there will be no further transformation possible. That is why martensite transformation is never complete. And so these three temperature lines tells you for the 1080 steel that how much percentage of the martensites you can form, and then remaining will be written austenite. Obviously, written austenite is not a good phase along with martensite, and that needs to be transformed later way. So that means what? Depending on the temperature to which I can cool, if I quench to a hot vial which is kept at about 200 degrees Celsius temperature, only 20% or 25% martensites will form. If we quench to a vial at temperature of 150 degrees Celsius temperature, then it will lead to 50% to 60% martensites. And once it is quenched below 100 degrees Celsius temperature, that is suppose at room temperature 30 degrees Celsius, then almost 98%, 97% martensites will form. So that is why in the industries, vial quenching, water quenching, polymer quenching, all different kinds of quenching are used. Vial quenching can be used to basically to create martensites, different percentage, again to temper it both, because as you know, tempering starts about 150 degrees Celsius temperature. So if we quench a steel to a vial bath kept at 200 degrees Celsius temperature, obviously austenite will transform to martensite, certain fraction of it, and those martensites can be again tempered by keeping it vial quenching. So vial quenching has both these advantages of making the certain fraction of martensitic formation and as well as tempering. Similarly, water quenching, which is done at room temperature, or brine, which is sub-zero temperature, or liquid nitrogen quenching, will be only to form more martensites, can be used. So that is why whenever more amount of martensites are required, we always use this. Polymer quenching is more advantageous that way, because polymer, as you know, once the steel is quenched in any polymer or water, polymer containing water, polymer actually high temperature heat, all these bunch molecules open up, it behaves like water. So it will take away more heat, and once the temperature goes down, the temperature of the sample goes down, it will behave like a polymer. So it will become viscous. So heat transport will be slower. So that has the advantage in the sense that polymer quenching can control the martensitic formation much better way than the water quenching. That is why nowadays in the industries polymer quenching is more extensively used, okay, because once the steel is dropped in the water, it is at high temperature, because it is quenched from high temperature. So it will behave like a water. So all the heat will be taken away. Water has higher heat capacity, and it is behaved like a fluid water. So therefore heat will be transported fast. The boiling will not happen much near the sample and the water, and once the sample temperature will cool down, it will behave like a polymer. It will not take away the heat so fast. So that is why the different kinds of quenching techniques are used to form different martensites. This is the main reason, because it is an athermal transformation. It depends only on the temperature to which it is cooled. It does not depend on the time at all. So there are many other features which are important to be discussed. Another feature is that, for martensitic transformation, important thing is the critical cooling rate, or what is literally known as CCR in the literature. The critical cooling rate has to be sufficiently low to be achievable. If it is very high, it cannot be achieved even quenching in water. Remember one thing very clearly: once a hot sample is quenched in water, this will temperature drop is something like about 1000 degrees. So such a large temperature decrease will lead to distortion of the sample because of thermal stress. So therefore the quenching rate has a lot of role to play to retain the sample shape. Martensite formation also will lead to relief on the surface, but on the top of which you have a thermal stress because of the temperature drop, and this can distort the samples extensively. That is why the critical cooling rate is very important. And normally plain carbon steel like 1080 steel has a large critical cooling rate, and that is why to decrease the critical cooling rate, alloying is done. Remember, alloying means putting different alloying element like manganese. Manganese leads to shifting of the nose to the right side. That is what is shown here. So nose of the C curve has been shifted extends to the right side. So therefore critical cooling rate, which is given by this line now, this is CCR, that is much lower. So only when I cool it faster than this one, then only I can achieve martensite formations. So that is possible. So this cooling rate, which is earlier one I used in the earlier plot, is no longer required. I can cool it this much, or I can cool it even much slower than that, and I can form martensites. Okay, that is possible. So one of the way of attaining lower cooling rate to form martensites is to alloy, to make the steel containing more alloys, alloying elements like manganese or even chromium can be used in the steel. So this is widely used in the literature. So therefore you clearly see that when you shift the nose to the right side, it also gives you a lot of advantage. Let me first remove these lines and then show you. It also gives you another advantage. What is the advantage? If you cool the steel, okay, if you cool the steel very slowly, it is just like a cooling 1 degree per hour. It's such a slow, very slow, because the slope of this curve is very low. Okay, that is what you see here. You can still form perlite. That is another advantage. That means what? Even when I take out the sample from the furnace and keep it outside, just by keeping on some hot plate, perlite can be formed. You do not need to cool it fast. So that is why alloy steel has more advantage in terms of the hardening, or in terms of basically these transformations are concerned. Similarly, if you cool it intermediately and keep it long time, baneits will form, but banetic formation here requires more time. You see here this requires about 10 to the power 7 seconds, that is quite large. So that way we do not gain much, because we do not want to keep it such a long time in the industry. It will, because industry time is money. So therefore the temperature time to which these samples are kept could not be so large. So for alloying additions, the banetic transformation is not good for alloying additions. Sometimes it is can be costly also. But for martensites it is very good. Martensite formation can be done very easily. Okay, again I am showing you this is TTT diagram for the 2.2% steel. Okay, that was initially first one was 0.8, then that was the intermediate one was when we add alloys, and this one is for the 0.2% steel. These diagrams has to be used routinely in the industries to understand the transformations. Here again it has two curves, actually three curves. 1%, 50%, 99%, and MS A50, M90 are shown. Okay. And on these then there is a dotted line here which shows you the 727 degrees Celsius temperature, that is U2 transformation temperatures. And they have different cooling rates are shown 1, 2, 3, 4 as you see here. So, 1 will lead to martensites, 50% martensites, okay. 2 will lead to martensites plus 2 is basically very interesting cooling. You quench it to about 250 degrees Celsius temperature and keep it there, and but do not go beyond these 1% perlite transformation line, but this will lead to benites then. Remember, then you quench it. But the advantage is this, once you do that, you reduce the distortion of the sample, because once it quenched directly from 727 to about 30 degrees Celsius temperature, you use a lot of quenching. So, what is done is much easier. You quench it to intermediate temperature such way that it does not lead to benitic formations, and keep it there, hold it so that temperature becomes uniform on the sample surface, distortion is less, then you quench into room temperature. That can lead to martensite transformations also, but without any distortion. And 3 is basically benites per martensites, that is also very interesting. You quench it to about 300 degrees Celsius temperature, keep it long so that benites form, lower benites will form, and you form only about certain percentage of the austenite to benite, and then remaining austenite which will be retained there, if you quench from 300 to about room temperature, this will lead to martensites. So, you can actually have a microstructure consisting of benites plus martensites together. That is possible because there are different requirements. As you know, the properties of the material depends upon the phases as well as so their volume fraction in the microstructure. So, these cooling these TTT diagrams still can allow you to control that, both the type of phases and also the volume fractions. This is one such. So, one can also have a diagram like that, you can cool it like this, keep it little longer and quench it. So, by doing that, this Mark 5, I can actually transform more austenite or transform austenite to more benites, and then remaining whatever maybe certain fraction 10 or 15% will be transformed to martensites by cooling that. Okay, that is the one other way. And now you can actually do different kinds of benites, you can actually cool it and do that, this will lead to upper benite, or you can cool it and keep it this and quench to water the upper benite plus martensites, and 3 or 5 will lead to lower benites for martensites. So, different kinds of morphology can be built into the microstructure. And the 4 which is shown here is basically leads to perlite, obviously, because you are cooling it down and keeping it at a high temperature 600 degrees Celsius temperature long time. So, as you will cross these nose, you will form perlite, as I told you earlier also. So, the moment you cross these curves, perlite is bound to form, because that is the most stable product in these systems. And then once a perlite forms, sample can be easily cooled, because once complete transformation of austenite to perlite happens, nothing else can happen, whether you quench it or you cool it slowly, does not matter. But normally it is quenched because or basically cooled rapidly so that the perlite which is formed at high temperature does not get changed at when it is investigated further. So, that means what these this is temperature versus time, each of these curves actually are cooling curves. Simply by changing the cooling curves, one can actually change all kinds of different kind of microstructure. So, that is what actually important you need to understand. So, real kinetics of these transformations will be discussed later, because kinetics means how actually mathematically the transformation happens, how the nucleation and growth affects, that is will be discussed separately as the kinetics of the phase transformations, because diffusional transformations are different types. We have seen precipitation, we have seen the Eutector transformations, and we are going to see some more. So, once all the diffusional transformations are dealt with, we will discuss about the kinetics of transformations separately. Now, as I told you that these 3 transformations, perlite, benite and martensites, are very common in the steels, and I discussed with you how this transformation do happen in the process of heat treatment of steels. But this is very difficult to explain to these people who are working on the shop floor. So, one of the way of representing them is using a TTT diagram, what is known as time temperature transformation diagram in the steels, correct. How these are actually used effectively in the actual applications, which I will be discussing in the next class, but I will tell you how this actually done. Remember that these transformations which are happening like perlite or benite or martensite by using different heat treatments, right. Perlite we are cooling it very slow, benite we are quenching intermediate temperature and keeping it longer there, martensite we are quenching to room temperature or lower temperatures from high temperature. So we are actually using different cooling rates, and these can be represented in time temperature plots, correct, because temperature versus time will give you cooling rates. If you draw different lines, these are slope of each line will give you the cooling rates. So therefore, we can actually use this cooling rate as a means of representing these phase transformations. But remember, these transformations will percentage or how much transformation will happen from the gamma to each of these phases, it depends on how actually the transformation process takes place. For a typical paralytic transformation, which is nothing but a diffusion control transformations, it involves both nucleation and growth with the distinct steps. The transformation will look like a C curve. Why? It's very easy to understand why it looks like a C curve. Remember the temperature scale is little bit odd here. So if I draw 727 plus 327, this become 1054 degrees Celsius temperature. So but it is showing something high here. So if I let us put this as a 1000, this is as a A1 temperature, and remove this temperature because they will be confusing to you. And this is a time scale in logarithm scale. So as you see, this is what is the 727 temperature for the steels. Now above 727 temperature it is gamma always. Only at lower temperature it transforms to some many products. So for the perlite, when it is close to 720 Celsius temperature, undercooling is low. So therefore nucleation and growth is very slow, correct. But remember diffusion is also very fast at high temperature. So therefore what will happen, you will have less number of perlitic, less number of lamellae present in the microstructure, but lamella will be thick because diffusion of carbon is good or high at high temperature. At low temperature undercooling is high, that means that when you cool it down to very low temperature, undercooling is very high. So therefore nucleation and growth both are actually sufficiently easily can happen, but diffusion is slow. So therefore the perlitic lamellae will be thinner in size, but the number will be high because undercooling is high, nucleation rate is high. So in between that temperature, somewhere high and low, there will be optimum balance of nucleation rate and the growth, obviously, because growth depends on diffusion, nucleation rate depends on the undercooling, growth also depends on undercooling, but on the top of undercooling it depends on the diffusion. As the diffusion is optimum at intermediate temperature, that is why the transformation rate will be very high at intermediate temperature. That is why you have a C-shaped curve. It is low, slowly increases and reaches a maximum, then it again decreases because of a diffusional problem. Because I told you two factors, one is the undercooling, other is the diffusion. So these two factors act in opposition, and that is why you have C-shaped curves. So we can actually make different C-shaped curves and then represent the transformations in different ways. Okay, just that is what is shown in the next view graph I show. Yes, you can see here that C-shaped curves, there are three C-shaped curves, two are solid, one is a dotted line, and this is what is the A1 temperature, or sometimes people write AE1 or AR1, but let us take it as A1 temperature, above which austenite, which is represented by A, is stable, below which austenite is also stable or metastably, okay. And you see here the C curves goes as a nose, and then there is a end to it, and let us not discuss what happens at lower temperature right now. So therefore we have a C-shaped curves going like this, and there is another C-shaped curve going like this, in between there is a dotted line. So we can say this is beginning of the transformation, this is ending of the transformations, okay. It only things to change is basically time. temperature is remaining same. Whether it is end or beginning, it does not depends on mass of temperature, it depends on the time. It starts at a time of about 10 to the power 2 seconds at lower temperature, but 1 second at intermediate temperature and at about 10 to the 5 seconds at a very high temperature. Okay. It ends also at 10 to the power 2 temperatures, at 10 to the power 2 at a lower temperature, sorry, it ends at a 10 to the power about 10 to the power 5 seconds again at lower temperature. Okay. So, that is but intermediate temperature it ends at a 10 second, you see here. So, that means at intermediate temperature transformation rate is very, very high, and that is true because intermediate temperature you have optimum balance of undercooling and the diffusion, that is what dictates the polarity transformations. Okay. On the other hand, as you look at lower, okay, as you look at lower temperature, you have parallel lines telling M50, M90. This is actually Martensitik's temperature. There is something known as MS. Remember, if I quench a steel, it will transform to martensite below certain temperatures. Okay, it will not transform at a high temperature because martensitic diving force required to transform martensites has to be present sufficient amount of diving force. So, MS is the transformation temperature, and then 50% and 90% transformation lines are given, because martensite happens in a very fast, that is why there is no time dependent on that, it only depends on the temperature. If you quench below this certain temperatures, only 50% or 90% transformation will happen, but it will happen like a burst, like a immediate kind of stuff. It happens actually speed of sound in the steels. That is why these lines are drawn like that. Now, I will stop here. We will discuss about different things here, different cooling rates, perlite, bainites and other things in the next lecture, and show you how these can be used for the steels to predict different microstructures for different properties, which is also shown on the right side of this table.